Hello everyone. I welcome all of you once again in this new lesson. So in this lesson we'll talk about parallax method to find distance between two faraway objects and a dimensional formula. So we'll start with parallax method first. So this method is used to find distance between two faraway objects. As in this case, we wish to find distance between some planet P and Earth. So let me explain the concept first. So in this method, we have to observe this distant object, so planet in our case, from the two different geographical locations on the Earth. So A and B are two different geographical locations on the Earth. And one more thing, so we need some reference point as well. So for reference point, we select a distant star whose position and direction from both the locations is almost the same. So here we have taken this S dash as our reference star, a reference point. So now again we observe this planet P from this geographical location A and calculate this angle phi 1. Again we observe this planet P from the different this geographical location B and calculate this angle phi 2. So remember, the position and direction of this reference star S dash remains same from both the geographical locations. So once we know the value of phi 1 and phi 2, so we can find this parallax angle. So this parallax angle is nothing but phi 1 plus phi 2. Now we know the parallax angle, and by using the formula theta equals to arc by radius, so we can find the value of S here. So S is the distance between A and P. So remember, so this is the arc, and this is radius, and this is the parallax angle. So therefore, if we know the value of this parallax angle and the distance between these two geographical locations on the Earth, we can find the value of S. So one more thing to remember in this case is, now if S and B are in meters, then theta should be in radians. Now we will see how to convert degree into radians. So we know that 1 degree equals to 60 minutes and 1 minute equals to 60 seconds. Now 180 degree equals to pi. So pi is 3.14 radians. So therefore 1 degree equals to 1.745 into 10 raised to the power minus 2 radians. So this is the relationship between degree and radians. Now if I convert this into minute, then 60 minute equals to 1 degree. So therefore 1 minute equals to 2.908 into 10 raised to the power minus 4 radians. So this is the relationship between minute and radians. Similarly, 60 seconds equals to 1 minute. So therefore 1 second equals to 4.85 into 10 raised to the power minus 6 radians. So now next we will see one practical applications of parallax method. So I have taken one question here. The moon is observed from two diametrically opposite point A and B on Earth. The angle subtended at the moon by the two directions of observation is 1 degree 54 minutes. Given the diameter of the Earth to be 1.276 into 10 raised to the power 7 meter, compute the distance of the moon from the Earth. So first of all, we will try to understand the question. So for that I have drawn a rough diagram here. So A and B are two diametrically opposite points, A and B on Earth, and our moon is here. So the parallax angle which is given here is 1 degree 54 minutes. So we are given the parallax angle and diameter of the Earth. So diameter of the Earth is 1.276 10 to the power 7 meter. So parallax angle is 1 degree 54 minutes. So if I convert this into if I convert 1 degree 54 minute into minute, then it is 114 minute. If I convert this into seconds, then it is 114 into 60 seconds. Now using this relationship, 1 second equals to 4.84 7 into 10 raised to the power 7 radians. So we can convert this angle from degree to radians. So the value is given here. Now coming back to the problem, so now we know the parallax angle, we know the diameter of the earth, so we have to find S here. So S is the distance between moon and the earth. So using the formula, angle equals to arc by radius. Angle equals to arc by radius. So if I put the values here, the distance of the moon from the earth is 3.84 10 to the power 8 meter. So now we move on to dimensions of a physical quantity. All the derived physical quantities can be expressed in terms of a combination of 7 fundamental or base quantities. So we call these fundamental quantities as the 7 dimensions of the world, so which are denoted with a square bracket. So dimensional formula for length is L, dimensional formula for mass is M, dimensional formula for time is T, current is A, temperature is Kelvin, luminous intensity is CD, and amount of substance is mole. So the main thing is, so once we know the dimensional formula for any physical quantity, then we can write that physical quantity in any system of units. Number one. Number two, once we know the dimensional formula for any physical quantity, we can convert it from one system of units to another system of unit. So we will see that in the next example. So let us take the case of area here. So area is a physical quantity. So it is a derived physical quantity. So we can resolve this area into its dependent physical quantities, that is area equals to length into breadth. So once I write area within the square bracket, now I have to read this as a dimensional formula for area. So dimensional formula for area is dimensional formula for length into dimensional formula for breadth. So since breadth is some form of length, so therefore dimensional formula for breadth is also L. So area equals to m naught L square T naught. So here now normally for any physical quantity we express its unit in terms of some multiples of m, L and T, which we will see later on also. But in this case, now since area does not depend on mass, it does not depend on time also, so therefore m component and T component is 0 here. So the powers are 0 here. So therefore area equals to, a dimensional formula for area is m to the power 0 L square and T to the power 0. So m to the power 0 and T to the power 0, it basically means that area does not depend on mass and time. Now see, now this is the dimensional formula for area. Now as I said earlier, once we know the dimensional formula for area, we can write the unit of area in any system of units. For example, in SI system, we measure length in meter. So it is L square here. So in SI unit, in SI system, the unit of area is meter square. Similarly, in CGS system, we write length in centimeter. So the in CGS system, the unit of area is centimeter square, and similarly in FPS system, it is square feet or feet square. So let me take one more example here. Force. So first we resolve force into its dependent physical quantities. So force is equals to mass into acceleration, as you can see here. Again, acceleration is a change in velocity divided by time. So now once I write force within the square bracket, again let me repeat this. So once I write force within the square bracket, then we have to read this as dimensional formula for force. So dimensional formula for force is dimensional formula of mass, a dimensional formula for velocity. So velocity is L by T, and dimensional formula for time. So this time component is here. So it is 1 by T. So therefore, a dimensional formula for force is m L square T to the power minus 2. Now, as I said earlier, in SI system, mass is in kilogram, length is in meter, and time is in seconds. In CGS system, it is in gram, so mass is in gram, length is measured in centimeter, and time in seconds. So now we can express force in any system of unit. For example, in SI system, its unit is kg meters per second square. In CGS system, it is gram centimeter per seconds to the power minus 2, and in FPS system, it is foot pound seconds to the power minus 2. So see, we can express force in any system of units once we know its dimensional formula. We go for one more example. Deduce dimensional formula for Planck's constant and write its SI unit. So energy equals to some constant into frequency. So this constant is called Planck's Planck's constant. So we have to find the SI unit of this Planck's constant. Now since H equals to energy by frequency, so resolving energy into its dependent physical quantities, so energy equals to force into displacement. So now here a dimensional formula for H, that is Planck's constant, equals to a dimensional formula for force into dimensional formula for displacement divided by dimensional formula for frequency. So dimensional formula for force, as we saw earlier, is mLt to the power minus 2. Dimensional formula for displacement is L. So dimensional formula for frequency is t to the power minus 1. So therefore a dimensional formula for H is mL square t to the power minus 1. Now once we know the dimensional formula for Planck's constant, we can easily write this in SI unit. So therefore SI unit of Planck's constant is, in place of m, now since we know that mass is measured in kilogram in SI unit, so we write here kilogram. Length is measured in meter in SI unit, so it is meter square, and time is measured in second in SI unit, so it is seconds to the power minus 1. So kg meter square seconds to the power minus 1 is the SI unit of Planck's constant. The next application of dimensional analysis is to check the consistency of equations here. So let us see how do we do this. So I have taken two examples here. So one for escape velocity. So the formula for escape velocity is square root of 2gm divided by r. So g is a gravitational constant, m is mass of the earth, r is the radius of the earth, and v is the escape velocity. So first of all, we'll look at the left hand side. So on left hand side we have v here. So dimensional formula for v is velocity is Lt to the power minus 1. Now we go to right hand side. So in right hand side we have this component. So here a dimensional formula for gravitational constant is m to the power minus 1 L cube t to the power minus 2. A dimensional formula for mass is m, and dimensional formula for radius is L. Now since this is constant, this 2 is constant here, so it does not have dimensional formula, so it is not written here. So on simplifying this, so we find that on right hand side we have Lt to the power minus 1. On left hand side also we have Lt to the power minus 1. So left hand side, so the dimensional formula of left hand side equals to dimensional formula for right hand side. So therefore this equation is consistent. So let us take one more example. So energy E equals to mc square. So this is energy, E is energy, m is mass, and c is velocity, velocity of light. So using a dimensional formula for energy, E equals to mL square t to the power minus 2. On right hand side we have mc square. So dimensional formula for mass is m, and c is the velocity of light, so it is L divided by t. Now since we have a square here, so it is L square t to the power minus 2. Again we can see that a dimensional formula of the quantity on the right hand side equals to dimensional formula of the quantity on left hand side. So therefore this equation is also consistent. So this is how we can check the consistency of equations using dimensional analysis. Now this is another application of dimensional analysis. So here we'll learn how to convert a physical quantity from one system of units to another. So before starting this, let me explain the concept. Suppose the length of this pen is 10 centimeter. So I can express the length of this pen in millimeter also. So if I express it in millimeter, then it is 100 millimeter. So I can also express the length in centimeter, in meter also. So if I express the length of this meter in meter, then it is 0.1 meter. So the point is, whether I explain the length of this pen in millimeter or centimeter or meter, the physical value of the length, it should remain the same. So it should not change. So this is the concept here. So Q is the physical value. So Q must be equal to N1 into U1 equals to N2 into U2. So N1 is the numerical value of this physical quantity in unit U1, and N2 is the numerical value of this physical quantity in unit U2. So just in our case, so if I write this in two system of units, suppose in CGS system it is 10 centimeter. So 10 is the numerical value and U1 is the unit. So that is centimeter here. Similarly, if I write this in SI system, So it has to be 0.1 meter. So 0.1 is the numerical value and U2 is its unit, that is meter. So the point is, whether I express the physical quantity in any system of units, the physical quantity has to remain the same. Now this U1 is the dimensional formula of this physical quantity in this system of unit. Now since we can write the dimensional formula as a multiple of m, l and t, so U1 is m1 into m1 to the power a, l1 to the power b and t1 to the power c. Similarly U2, now U2, the dimensional formula for this physical quantity in this system of unit U2, so U2 is m2 to the power a, l2 to the power b and t2 to the power c. Now if I use the value of U1 and U2 in this expression, so I can arrive at this expression. So therefore N2 equals to N1 m1 by m2 to the power a, l1 by l2 to the power b and t1 by t2 to the power c. So let me explain this conversion once again with this example. Suppose if we want to converge 1 joule into erg. So remember, joule is the SI unit of energy and erg is the CGS unit of energy. So I have to convert 1 joule into erg. So here the physical quantity involved is energy. So the dimensional formula for energy in terms of m, l and t is ml squared t to the power minus 2. Now if I compare this equation and this equation, the value of A is 1, the value of B is 2 and the value of C is minus 2 here. Okay, now next we have to use this equation. So M1 is the unit of mass in SI system. So in SI system we measure mass in kilogram. So since we are converting this from SI to CGS, so I convert this kg into gram. So 1 kilogram equals to 1000 gram. So L1 is the unit of length in SI system. So in SI system we measure length in meter. So if I write this in centimeter, then L1 is equals to 100 centimeter. So similarly, time in SI system we measure time in seconds. So it is 1 second. And N1 is the numerical value of this physical quantity in SI system. So in SI system the numerical value is 1. So the value of N1 is also 1. In CGS system again we measure mass in gram. So we measure length in centimeter and we measure time in seconds, and we have to find the value of N2. So if I put these values in this equation, so which I have shown here, the value of N2, the value of N2 is 10 to the power 7. So therefore 1 joule equals to 10 to the power 7 erg.